Over the last few lectures, we are talking about one-dimensional unconstrained optimization. In such optimization, the design vector is one-dimensional, which means it is a scalar. Now we'll go toward multidimensional unconstrained optimization, where the design vector will be at least a two-dimensional vector. In this lecture, we'll look at the elementary theory as well as couple of examples of multidimensional unconstrained optimization. And in subsequent lectures, we'll talk about the numerical techniques to solve such problems. In multidimensional unconstrained optimization problems, we are interested in minimizing y, which is a function of x, where this x is an object in Rn. That means this is a real space n-dimensional, which basically means that x is an n-dimensional vector going from x1, x2 to all the way up to xn. Usually we take that as a column vector, therefore we have used this sign transpose here. F is a function that takes an object from Rn, that means an n-dimensional vector from real space, and gives back an object in R, that means it gives a real scalar. Now, for such problem to have a local minima, the necessary condition is that for x star to be a local minima of fx, the gradient of f at x equals x star is a null vector. Now, of course, this necessary condition is not enough, so we have to look for sufficient condition, and in sufficient condition, we see that apart from this necessary condition, we have one additional requirement, and that is the del 2f x equals x star should be positive definite. Now, what does that mean? To see it, let us go through the definition of gradient, that is del f, which is an n-dimensional vector. Each of its element is a partial derivative of f with respect to one of the component of this design variable x. So first one is del f del x1, then del f del x2, all the way up to del f del xn. Del 2f is something that we call Hessian, and Hessian is an n by n matrix. In this matrix, every element is a double derivative. So first one is del 2f del x1 2, then del 2f del x1 del x2, etc., etc. Last element of first row is del 2f del x1 del xn. Similarly, in second row, del 2f del x2 del x1, then del x2 2, all the way up to del x2 del xn. In last row, starts from del xn del x1, del xn del x2, all the way up to del xn2. Now, for the matrix being positive definite, we know the definition of that is that if we have a vector y in Rn, which is not a null vector, for all such vectors, yt del 2f y should be greater than 0. Now, this is a condition not very easy to prove for any particular matrix. So, what we find that if a matrix is indeed positive definite, then all eigenvalues of that matrix will be positive. We can prove that for a given matrix, but if the matrix size is very large, it becomes sometimes very problematic to get all the eigenvalues. For the case where we have a 2 by 2 matrix, that is n equals 2, then there is a condition, we call this Sylvester criterion, what says that this del 2f matrix will be positive definite if the determinant of this matrix is positive and the first element, that is del 2f del x1 2, is also positive. If this Sylvester criterion is satisfied, then we know that this matrix is positive definite. This helps us at least to take up the problem with n equals 2. Now let us see this example. Here we are interested in minimizing this function fxy, which is x square plus 2y square minus 2xy minus 2x. Here this vector x is xy, two elements, and x star, where this function fx will be minimized, that location is x star, y star. Now to check this function is at all minimized or not, or if it is, where it is minimized, what is the value of function at that particular point, we have to find out the gradient and Hessian of this function f. So for the gradient, we need this del f del x, del f del y transpose, and for Hessian, we need del 2f del x to del 2f del x del y and del 2f del y to all these derivatives. So here del f del x, we can find it out. There we have x squared, so twice x. Then del f del x of 2y square goes to 0. For negative 2xy, I get negative 2y. And for negative 2x, I get only negative 2. Similarly, del f del y, we can take this part will be 0. Here I get 4y. Here I get minus 2x, and that's about it. So I have 4y minus 2x, which gives me the gradient is 2x minus 2y minus 2, 4y minus twice x. To get the double derivative, first of all, I take the another derivative of del f del x, and I get del 2f del x 2 equals 2. Similarly, I take a derivative of this with respect to y, and then I get, because of this negative 2y, I get minus 2. Similarly, here I need this double derivative of f with respect to y. If I do so, then I'll get 4. So now I can plug in all the values over here, and I get this 2, negative 2, negative 2, 4. Now we look at this gradient 0, and this gradient, when it is 0, it gives us this 2x star minus 2y star minus 2 to be 0 and 4y star minus 2x star to be 0, which if we solve these two equations will give me the values 2 and 1. So now we have to see that at this particular point 2, 1, this function will take its maximum or minimum. So for that, we'll check this determinant of del 2f, and it gives me 12. And then del 2f del x2 is anyway 2. So both are positive. Therefore, this matrix is positive definite as per the Sylvester criterion, which tells us that at this particular x star y star 2, 1 will have a minimum. And I can plug this value 2 and 1 in this function, and I get a value of negative 2, that is the minimum value of this function, considering x and y both are real. Similarly, I take an example of regression where through these 3 points, I am fitting a line y hat w0 plus w1 by x. We have to see that if the cost function indeed has a minimum here. To see that, I write this cost function e as 1 by 3. We have 3 points, summation of 1 to 3, and yi minus w0 minus w1 xi whole square. I can expand this putting the value of xi and yi, and it will come like this: 1 by 3, 3 w0 square, 41 by 36 w1 square, 3 w0 w1, etc., etc. Now if I set this gradient to be 0, it will give me two equations. Two equations are coming from del E del w0 and del E del w1 to be 0. From these two equations, if I solve, I get this w0 is 5.14, w1 is 1.71, and I have the value of E at this particular point is 30.86. Hopefully this is minimum, but we have to check if it is minimum at all. For that, we have to check the Hessian. Hessian, if I take these 4 elements of Hessian and I evaluate from this del E del w0, del E del w1, then I get this element in this matrix 6, 3, 3, 41, 18, which tells us that the determinant will be 6 into 41 by 18 minus this 3 into 3, which is 14 by 3, which is a positive. And the first element of this matrix is anyway 6, so that is positive. Therefore, Sylvester criterion is satisfied. So it is indeed a minimum. We can write that our regression will be y hat 5.14 plus 1.71 divided by x. So now to summarize this part of our lecture, we have discussed the optimality condition for multidimensional unconstrained optimization and solved example problems. For your exercise, you check for this function fxy x square plus y square if there exists a minimum. If it does, then find the minimum. That's all for this lecture. Thank you, and I'll see you in next class.